Today we're going to begin section 5.3 and look at exponential functions, right? So we're going to start with an exponential graph, and then we're going to learn how to write exponential functions. So start, right? You might not remember what an exponential function looks like, but just remember you can graph almost any function with a table of values, right? So we're graphing the function y equals 1/2 times 3 to the x. It's in the form of y equals ab to the x. This is exponential because the variable is an exponent right here. So to start, we're going to just create a table of values, right? So, it's always a good idea if you don't know what the graph is to first, start selecting x values around 0. Just as you would graph a line or a parabola in the beginning. So I choose the values, integer values right now. And I'm going to substitute them into the function, and now I have my output values. At this point, what we want to do is go ahead and just plot our information, right? So got my graph showing up here before my table of values, but so we go ahead and we plot our points and we sketch a curve in. And what in the beginning, you really don't know much of what the curve looks like until you've been exposed to them. But this is the exponential type growth graph. It starts out as we move from left to right. You can barely see it here. It's almost touching the x-axis, and it's slightly increasing vertically as we move to the right. And then all of a sudden, it starts to grow exponentially due to the fact that each point on the curve is being generated by a multiplication of 3 from the previous value. Okay, things about exponential functions that we may not remember. I said this curve, as we move from left to right here, it's almost touching the x-axis, and in fact, it never actually touches the x-axis. That's what we call an asymptote. So this red dashed line is a representation for an asymptote, and every time we graph the function, we have to include this dashed line to indicate that there's an asymptote there, and we often indicate the equation of the asymptote. So for exponential functions, we have horizontal asymptotes. They always take the form y equals wherever the asymptote exists here. Other things we should point out are domain and range we've forgotten about or haven't thought about in a while. So the domain of the function is going to be the set of all input values. So even though there's an asymptote here, there's nothing stopping me from putting smaller and smaller and smaller input values here into the function to obtain output values. Those output values are going to get closer and closer and closer to 0 as the input values get smaller and smaller, but nothing stopping me. I can put negative infinity into this function and still get some fraction of an output that's greater than 0. And same with as the input values get larger, this graph is just going to, continue to exponentially grow towards infinity. Nothing will ever stop it from the horizontal side on either side of 0. So we would say the domain of this function is all real numbers. The range, however, is different. This graph grows vertically forever, but it never actually gets down to 0 and never crosses this asymptote. So we would say that the range is all values greater than 0. Not greater than or equal to, but greater than 0, right? And this is our notation for it. Okay, so exponential functions, right? Just another quick summary here. We'll spend most of our work analytically, but we want to expose you back to, what an exponential function is, right? So we have growth and decay models. They both use the same format, y equals ab to the x, where b is similar to the 1 plus r, 1 minus r in the, if you want to call it a formula, the exponential growth and decay models we've worked with in section 5, 1 and 2. A is the initial amount. That's same as our a sub 0 value. And it's also the y-intercept, assuming we're in this format right here. Meaning if x is 0, b to the 0 is 1, your output would be a. So this initial value here is always going to be your y-intercept when we're working in an exponential function in this form, ab to the x. B is your growth factor. It's your multiplier. It's your base. And this is the same value that we found by adding 1 to r or subtracting r from 1 in the previous model. And y is your final amount. X is the measure. It's often a measure of time, Bounces would be more of a exponential sequence, or a geometric sequence is what we call it. But the input value in context situations is time. So exponential growth, similar to the warm up, looks very similar to it. Y-intercept is a comma 0 comma a, excuse me. There's a vertical asymptote here in red with the equation y equals 0. All of the horizontal asymptotes with these exponential functions in this format will have the form y equals 0. Exponential decay, as x increases from left to right, the function decreases rapidly, and then eventually it slowly starts decreasing towards 0, and that's due to the the exponential growth factor there. Same thing, the y-intercept here is 0 comma a. Again, that's this a value in the equation, assuming b is your growth factor or decay factor at this point. Two things you want to know about growth. The b value must always be larger than 1 to be an exponential growth. It's the only way to increase values by repeated multiplication. You have to multiply by a number larger than 1. And we're also always, you're going to work with an a value of 0 to take this format. If the a value is negative, the graph would be inverted and kind of work down this way. Now, exponential decay here, the critical thing here is that your multiplier, your growth factor, needs to exist between 0 and 1 and be positive, right? Both of these base values have to be positive when we're modeling exponential growth and decay functions. So, again, to decrease a function through repeated multiplication or repeated division, that base there, it needs to be a positive number, but it needs to be less than 1, greater than 0. And that's the only way to decay it with repeated multiplication. And b cannot equal 1 in this case. Also, a is going to be greater than 0.